This is sample exam 7, question number 10. Let x and y be continuous random variables with joint density function f of x y equal to 12x, y between 0 and 2x less than 1. What is the conditional density function of y given x? So question 10, we're asked to find the conditional density function, and so that is by definition this. So we are given the top and we need to find the marginal of x. So here is a plot of the joint density of x and y that we're less than x equal half, and this is a line of 2x, y equal 2x. We're in this region. So to integrate out y, we go from this function to 0. So f of x, you integrate from 0 to 2x of our joint density, and it equals this. We get 24x squared. So f of y given x is the joint, which is given in the problem, divided by what we just solved, which is 1 over 2x for this region. Number 11. Let x and y be independent random variables, each with density f of t equal to 1 over 2 theta for t between negative theta and 0 otherwise. If the variance of xy is equal to 64 over 9, then theta equals, number 11, we want to find the variance of x, y. Now, by definition, that is equal to the expected value of x, y minus the mean of x, y, quantity squared. And then there's a simple formula or relationship that says the expected value of x, y squared minus the mean. But since they're independent, you can separate them. So this should be the expected value of x, y, but you can separate. And since x and y are independent, we get this. So if we can find the each of these components, we will be finished. Now, since x and y have the same distribution, then the expected value of x squared is equal to the expected value of y squared. So we'll just find this one, which says stick in y squared times the density of y, integrate from all possible values, and we get theta squared over 3, and that's for both of those. Now the expected value of x and y are the same because the same distribution, so you plug in y over times its density, integrate over possible values, you get 0. So this piece of the formula drops out. So the variance that we're looking for is just the product of these. So that's what we do here. The variance is expected value of x squared times expected value of y squared, which is this, which is that. So so theta to the 4th is 64, which implies that theta is 2 radical 2. Number 12, let x and y have the joint density function f of x, y equal to x plus y, x between 0 and 1, y between 0 and 1. What is the probability that 2x is less than 1 given that x plus y is less than or equal to 1? Problem 12, they ask us to find this probability, which by using the relationship of conditional probability, it's the intersection of these divided by what we're conditioning on. So if we find this piece and then find this piece, divide them, and we're finished. So first of all, let's plot the region for this. So this line here is the x plus y less than 1, which is what this is. So take the x over to the other side, and it's this region. So we'll find the probability of that. And this one is the joint. So this is the same as x less than or equal to a half, which is this region. So the top is this area, and the denominator is this area. So let's find this region first. So if we were to integrate out x, we'd have to go from here to here, and then at this point add it to this region. But it's not as convenient as if we integrate out y first and then go from 0 to x on 0 to 1/2 on x. So we'll integrate out y first, and we go from 0 to this function, which is 1 minus x, or minus x plus 1, and then the x goes from 0 to 1, and so we get this, and then this, and that equals 11/48. So now we have to find the denominator, which is that whole region, and so we're going from 0 to 1 minus x, and then 0 to 1. But this first integral here is exactly what we did here. Okay, so we can skip down to here, and instead of plugging in 0 to 1/2, we plug in 0 to 1. And if you want to do this again, you can, but I'm skipping it, and we go from 0 to 1, and we get 1/3. So the probability is this numerator divided by the denominator, which is 11/16. Number 13, let the random variable x have moment generating function m of t equal to 1 over 1 minus t squared for t less than 1. Find the expected value of x to the third. Number 13, we're asked to find the expected value of x cubed, given that this is the moment generating function. So we take the first derivative, the second derivative, the third derivative, and so the expected value of x cubed is the third derivative of the moment generating function evaluated at t equals to 0, which is 24. Number 14, let x and y be continuous random variables with joint density function f of x y equal to 4x, 0 less than x less than square root of y less than 1. What is the marginal density of y where non-zero? In number 14, we're asked to find the marginal density of y. So to me, I am a visual person, so I always like to draw the region. So here we both x and y are between 0 and 1, and this relationship, which is this. So it's y is greater than x squared. So we're up here. So to find the marginal of y, we have to integrate out x. So we go from 0 to the square root of y. So here's our joint. Take the antiderivative, evaluate it at its limits, we get 2y, and y is between 0 and 1. Number 15, if x is a random variable with density function equal to 1.4 e to the minus 2x plus 0.9 e to the minus 3x, x greater than 0, then what is the expected value of y? Now number 15, it said we want to find the expected value of y. The expected value of x. And so we take x times its density, which is given, over the limits of the variable, which is this. So we're going to integrate this by parts. We're going to let u be x, which implies du dx, and this is going to be dv. And then the antiderivative of that is this. So it is uv integrated at its limits, and then it is vdu, vdx. So we get this. Now, these exponentials here with the negative exponent, when you evaluate it at 0, those will dominate this x. So this number goes to 0 when you plug in this. And when you plug in x equals 0 there, you get 0. Goes away. So the antiderivative of this is that. Antiderivative is this. Evaluated 0 to this. Now, when you plug in infinity, those get really, really small. Actually, they go to 0. And then you plug in 0, and that's a 1, and that's a 1, so it's minus, plug in 0. You get, I skipped a step from up top. So you get negative, or 0.7 over 2, which is what this is. But when I was doing the homework or doing this, I skipped a few steps here and just copied and pasted down here. So 0.7 over 2 is actually the same as this. This is 0.1, and the answer is 0.45. Problem number 16. In a certain communication system, there is an average of 1 transmission error per 10 seconds. Let the distribution of transmission errors be Poisson. What is the probability of more than one error in a communication 1/2 minute in duration? Number 16. We're given that we have a Poisson process of 1 error per 10 seconds. We want to look at 3 10-second spots, or a half a minute. So that means this combined is Poisson 3. We want to find the probability they have at least or more than one error, which is 1 minus that we have 0 errors minus that we have 1 error. Plug it into the Poisson formula. We get this. Those combine to be minus 4 e to the third. Number 17. Let x1 through x9 be a random sample from a normal distribution with unknown mean and unknown variance sigma squared. Let the sample mean equal this and s squared equal that. What is the probability that x minus mu is less than 0.62 times the sample standard deviation? Now, number 17, we're asked to find this probability. We're from a normal distribution, unknown mean, unknown variance. So if we divide both sides by s, we get this. Then we multiply both sides times the square root of n, which is what this is. Remember, if you invert this and multiply, it's square root of n is in the numerator. So n is given to be 9, so that's 3. So 3 square root of 9 is 3, so 3 times that is 1.86. This is a t distribution with n minus 1 degrees of freedom, so it's 8. And if you look that up in the table, you get 0.95. Number 18. Let x have a Poisson distribution for x equal to 0 to infinity, 0 otherwise, where theta is greater than 0. If x is an observed value of the random variable x, what is the likelihood ratio region for testing the null hypothesis that theta is equal to 1 against the alternative hypothesis that theta is not equal to 1? So number 18, we're in a it's asking us to find the likelihood ratio critical region. So we are given that it's a Poisson distribution, and we're taking a sample of size 1. So the log likelihood of a Poisson is this. And then we take the derivative of this log likelihood, set it to 0, we get theta squared is equal to x. So now when we find the critical region, now this is really an abusive notation, because the likelihood ratio, we need to find the maximum of this function over the null hypothesis, but it's only one value, so it's theta equal to 1. And then the maximum of this over the alternative region, and that's what we did here. It's theta squared is x. So really we need to put like the supremum or the maximum overall value. So this ratio is, here you have to plug in theta equal to 1. And here we plug in our maximum over the alternative, or I mean over the whole set, not the alternative region, and which is x, which is here and here. So those cancel, and 1 to anything is just 1, so that kind of goes away. If I bring up the x and bring this up, we get this. Now if we take this to the other side, we get this quantity is less than or equal to k squared. And I would have stopped, but that's not a possible answer. So we have to take the reciprocal of each of these, which flips this, and you get this quantity here. So this is the rejection region. And again, this is over the whole sample space, and this is over the null hypothesis. Well, I hope you enjoyed this video. If you did, please like it. Subscribe so you don't miss the next one. We're going to keep going until we go through all 8 exams. Thank you. Bye.